In this video, I will teach you how to use the FuncAnimation in Python. It is a function that is often used to make simulations and animations in Python. For example, this one, this one, this one, and this one. These are actually all examples I treated already on my channel. But on this video, I will focus solely on this FuncAnimation right here. So how you can use it, its arguments, and basically everything you need to know about it. Let me help. Right here. Let me put myself right here. I don't know if it was a good idea. Anyway, so using the FuncAnimation in Python for making animations. Now, when animating plots in Python, you gotta use the matplotlib.animation.funcAnimation. If you don't have Matplotlib, it's very easy. You do a pip install matplotlib. Okay, now I already have it installed, so you're good to go. Now, in a way, the FuncAnimation is a function provided by Python to help you animate stuff. Now we can see the official documentation of Matplotlib, so it's the matplotlib.animation.funcAnimation. It takes all of these arguments. We'll discuss the most important and the most relevant ones. The most relevant ones are these 6 arguments right here. So it's a figure, a func frame, init func. Well, this one is not very much important, and f-args and interval. Alright, so we will see a practical example about all of these arguments. We have another optional argument called blit and some methods. Alright, so you see here I've provided a core structure of how to use this function, but we will see this together step by step. So, first step, import the libraries. So import matplotlib.pyplot as plt. This is to do all the simple plots or advanced plots. And then to import the FuncAnimation, you do from matplotlib.animation import FuncAnimation within capital F and then capital A. Now let's consider a very simple example of simulating a sine wave. That's very easy. Okay. So first of all, whenever you want to animate something, now you see an animation or a simulation is the change of an entity across time or across space, for example. Let's consider the variation across time. We will first define a vector that represents the time points. I call it t is equal to np.lengthSpace from 0 to 10 across 100 points. And since we are using the numpy module, we gotta import it. So I do an import numpy as np. And then we define a simple sine wave. So let me call it y is equal to np.sine of t. Now let's try to plot this like we usually do. Usually you do a figure and then x is equal to plt.subplots, and then you do axis.plot of t and y, for example, and then you finish with a plt.show. We run this code. See, we plotted this result right here. Now, what I want to showcase you with this example is make a graph that starts from here, so there is just one dot, and then you see slowly the sine function being built. To do so, we are going to use this FuncAnimation function. So let me remove this one, and let's move down here. Let me hide this, and let's go. So we are going to create a variable called animation is equal to FuncAnimation of something. Now, let's go back here. We see that this FuncAnimation takes as input, first of all, a figure. So in a way, this is our input, so it takes in our figure. What you can do also is do like this, and then say fig is equal to fig, right? And slowly build the arguments. The second argument is a function that updates our data. Okay, so let's define a function. We define a function, so def update, okay, of something, and then we do a pass. Now, this function right here, if you go back to the documentation, states that it is a callable function that requires this signature, where the first element or the first argument must be frame. Alright, so let's do here frame. Now, this function right here actually will draw our plot each time at this frame right here. For example, at frame equals 0, we will have a plot. At frames equals 1, we will have a plot, and so on and so forth. We do a return. We are going to return a something. And this something is going to be here. Let me call it animated plot. Will be equal to an axis dot plot. Okay, like so. Now when you do this, and let me actually print animated plot. So this is the plot that we are going to animate. If you do this, let me just remove this for now. Let's rerun the code. You see here we got an array, but we want to extract the element of this array. To do so, you simply add a comma right here. If we rerun the code, you can see here that now we have a line 2D. Okay, very good. So let me close back this, and let's go back to our FuncAnimation. In this function right here, update data, we are going to return this animated plot. We can specify here that func is equal to update data. Inside here, we update the data. We do a animated plot dot set data. So this function right here, dot set data, will actually update the previous plot with our current data. And our current data is going to be, let's consider for instance t and y. All right. Now we have figure and func. The third was the frames, so it is the total number of frames. Here you can do frames is equal to the length of t. For example, here we will have 100 frames. This was the first argument. The fourth argument is the additional function arguments. Here we don't have additional arguments to set in, so we will not be needing this one. And then interval is the delay between each frame in milliseconds. We can say, for example, that interval, we have 25 milliseconds between each frame. Alright, so if I run now this code, you'll see that here it starts from 0, 0, which is normal, but then the plot isn't looking quite right. This is because we have to actually set the limits of our plots beforehand. I can do an axis here, axis.set xlim. For example, here I set it the x limit between the minimum value of t and the maximum value of t, which represents 0 and 10. And the y limit is between -2 and 2. If I run again the code, we'll see now we have our sine function. Now this function is not being animated, because here we are updating it and each time with the entire array. What we want to do is, instead of updating it with the entire array, we are just going to update it, for example, from the frame 0 to the frame 50. And then from the frame 0 to the frame 100, frame 0 to the frame 105, etc. To achieve this, here it's very simple. You do a brackets for both of them. And then we want to have all the elements before frame. And like so. For example, here, this means that if frame is equal to 1, we are going to get 1 dot. If frame is equal to 10, we are going to get all the elements from t0 to t10. And then if frame, for example, is equal to 1000, we are going to get all the elements from t0 to t1000. If I run this code, you'll see that now our sine is updating. If you want this animation to stop when it reaches its end, you can come back here to the documentation. You can see there is a argument called repeat, is a boolean. If we set it to false, so let me come back here. And we set repeat is equal to false. Okay, let's run this. You see that now it is animating. And then when it reaches the final value, it stops updating. It stops repeating. Okay, let's actually remove this. Now let's say we have this animation right here that we want to save. All you gotta do is make an animation dot save. You specify the name of the file. For example, animation sine.gif. Alright, I save the code, I run it. Now you can see that here we have our plot. It is working perfectly fine. But we have also a GIF right here. So if I open this, you can see here is our GIF. That's very nice. Alright, so here I've prepared a second example about the mass spring system. Let me just copy this to show you what it does and paste this. Alright, so if I run the code, you'll see that we get this plot right here. Here you have the mass oscillating between the origin. Then here you have the displacement of the mass at each moment t. And you can see here it is slowly getting damped. Now we are going to see how we can make this animation out by ourselves. Alright, so let me remove all of this all the way up here. Now you see here, this is the solution to the differential equation of the mass spring system. It is very straightforward to get, so we will not waste any time trying to understand this. So let's start off here. Suppose we have our displacement. We can start by initially plotting it. So doing a figure axis is equal to plt.subplots, exactly like we just did. Then we do an axis.plot, t and x. And do not forget to do a plt.show. plt.show. Okay, we run the code. Now you can see we have this plot right here. Now this is interesting. But we want to see like the mass moving from left to right. This is surprisingly easy to achieve actually. Now again, let me go back here. Let me copy this one. This will be my foundation. So I copy down this. Then I paste it right here. So we just created and defined all the data that we want to animate. Now we create the axis, so fig axis, our animated plot. Now, the x limit will be set between -2 and 2 because this is in a way the interval where our mass will oscillate. So I can do -2 and then 2. And for the y, we can do as well -2 and 2. Since we have only a variation across the x-axis, we didn't speak about the y-axis. It doesn't quite matter. Okay, so let me remove this. We set the grid. Now, we do our animation function right here. Now, to set the data, so we have a dot. The mass will be represented as a dot. This dot will be moving from left to right. To achieve this, you can specify here, we have x, okay? We know that the y coordinate of this dot will not change. It is always on the same line, but it is the x coordinate that will change. So in a way, we can say that x, y will be still a 0, and then x will be of frame. Now remember here x is a 1D vector, so if we do x of frame, this will return a value. Let me actually specify the other arguments. So, alright, so if I run this code, you'll see here that we will have a problem. Because what we are passing right here should be an array. It shouldn't be a float or an integer. So if I do this, specify it simply by an array, and then same goes for this one. I run the code, I close this, and then run the code. You can see here we are not looking at our dot, because we have to actually specify first, initially here, a marker size. Let's say we have a marker size of 4, and the color is equal to red. Ah yeah, and let's specify the marker to an O. So I rerun the code. Now you can see that we have this little dot moving left and right. Let me actually set the damped factor to 0, so we can have a never-ending oscillating thing. And let me set this marker size to 20. Alright, now we have our dot moving from left to right. Now to add the line, you see here, the first point of the line will be this one. This point will not change. It is between -2, 0, and it will be attached to this mass right here. So it's in a way the x of frame and then 0. So let's actually draw a line. Instead of calling this animated plot, let me call it animated mass. Let me do here an animated spring. Okay. So this will be animated mass, and this will be animated mass. For animating the spring, we are going to represent it by a line. This line starts from -2 and then x frame. So here in this spring animated, the arguments we are going to specify here are only the color. We are going to set this to blue. And then when updating it, like so, here, we do an animated spring. Okay, so let me remove this and this. Here in this first argument, we're going to specify the x0 and then x1 of the line. And then here it's the y0 and y1. Now remember, the y does not change. So here it will be starting from y0 and ending at y0. Now for the x value, it starts from -2 and it ends at the current position of x. So it starts at -2 and it ends at the current position of x. So this one right here. If I go ahead and run this code, you see that now, in a way, we have a spring attached to this mass right here. You can also go ahead and return this. Now, to add like the effect of a spring where the smaller the distance is, the more compressed the spring is, and the greater the distance is, the more, let's say, stretched this spring is. Straightforward. Animated spring dot set line width to something. Now this something here, I've specified it. Let me take a look at this one. Let me just copy this and paste it right here. So we do an x frame -2. So let me actually run this to explain it at the same time. Here. Why do we do x frame -2? Because you see here, when x is equal to -1, the line width should actually be the maximum value. If x is equal to -1, so we have -1, -2, which is equal to -3. The absolute value will be equal to 3, and then times 2, like just a scaling factor, will make the total line width to 6. So this is when x is equal to -1, which is the biggest value for the line width. Now if x is equal to 1, we have 1 -2, which is equal to -1, and then the absolute value is 1 times 2 is 2. So we have, in a way, our line width, the interval of our line width is between 6 and 2. 6 being the extreme left, and 2 being the extreme right, right here. Alright. So if you want to have the line, the spring line below the mass, we can just swap these two lines. Okay. Now if I run code, you can see here, now we have the dot on top of the spring. Very good. Now we want to add, just by this right here, another plot displaying the displacements across time. Okay, so let's do this. We have here specified a plt.subplots. We want to have one row and two columns of plots. And then here I specify this to 0. And then same goes for this one, and then this one, and this one. Grid to axis 0 of grid. So, okay, so now if I rerun the code, you'll see that the grid is applied to this plot right here. Here we are going to display the displacements with variation of time. I can call it, let's call it animated disp for displacement. So we are going to draw on the other plot. So we specify an empty array for now and make it a color, let's say red. Okay. And then here we specify the limits, making sure to change the index every time. Okay. The x limit, again, here will be the minimum of the time and the maximum of the time. So I can do here min t, then max t. And then the y limit, we know that the mass will oscillate between -1 and 1 maximum, so we can leave it at -2 and 2. Okay, we update here our plot doing a animated displacement dot set data. This will be exactly like the sine wave we just saw. We have on the x-axis the time until frame, and then on the y-axis we have our displacement x. So x until frame. So, and then we can return our plot. Okay, we run the code. You can see here list. Yeah, you see here list object has no attribute set data. This is because I forgot to specify the comma here, because axis1.plot returns an array, but we want to extract the element within this array. We do this by adding this little comma right here. If I rerun the code, you can see here is our beautiful plot. Alright, so let me actually close this. You see, there is also another parameter we didn't speak about right here. This is the blit. Blit, in a way, is an argument that will optimize the drawing. You can add it if you want here, so I can do blit is equal to true. Okay, now is there anything else we can do? We can, for example, change here the damped factor. Let's make it back to 2. We run the code, and we can see that now our system is slowly being damped. Okay, we can make it even greater. Like, let's make it, let's say it's equal to 1. You can see here our system is very damped, so it quickly goes back to its initial position. Now I can reset this, for example, to 0.6 and make a bigger spring, like a stronger spring. You can see here the oscillations are quicker and eventually going to 0. Again, if you want to save this very nice looking animation, come them all the way down here. You do an animation dot save, specifying the name of the file, for example, full animation dot diff. I run the code. We see our window right here. We wait for the magic to happen. It's about to happen, the magic, just wait. Eventually, this beautiful GIF will pop up. Give it just a little bit time for it to prepare. Then there you have it. Let me hide this, we don't need this. Here's our magnificent GIF. Beautiful. So, with that, this concludes our video and my teaching on the FuncAnimation function. I hope you understood, you followed well. If you have any question or anything wasn't clear, let me know in the comments. I will answer it. I'll break legs and bones to answer your question. Just make it clear, please. Preferably in English, but that's not necessarily. If you want to apply the knowledge you just learned, you can try simulate this in Python. I happen to have videos about them. If you want to check them out, I highly suggest you. So, thank you for watching. This has been Yunus, and peace.